Around the engine. As you can see, this is a three-wheel dolly that has a fuel tank mounted on it, and it has an engine mount, and there's the back of the 084. What I wanted to show you here was the components of the fuel injection system. Now, don't pay a lot of attention to the wiring. I did not want to cut this wiring harness. I wanted to leave it where I could use it on an airplane, so if you'll notice the wiring, I've just coiled the wires up and zip tied them. But I wanted to show you the basics of the system. Of course, we have the fuel tank. Fuel comes out of the tank and goes to this inline filter, and then it goes into the bottom of the fuel pump. It's suction on the bottom, but once it comes out the top, it goes through a fuel filter and then comes on up and goes to the fuel rail here. This is what's called a fuel rail. There's pressurized fuel sitting here, and if you look on the back of this fuel rail, you'll see the injectors. There's one there and there's one there. So there's an injector for each cylinder, and I'll back up a little bit so that you can see. But this is the intake manifold, and then here there's been a fitting welded onto it for the injector to fit in it. So here is pressurized fuel that's sitting on the back side of this injector waiting for the signal that comes down this wire from the engine computer to tell it to open and close at the correct time. If we follow the fuel flow on around, this is a tube that takes fuel on over to the other fuel rail on the opposite side of the engine, and it's set up the same way. There are two injectors, one for each cylinder. So fuel, once it comes through the second fuel rail, now it's returned to the tank, and you'll see that hose coming down, and it's going down to this fuel pressure regulator. Now, a close-up of some of the components. There's the electric fuel pump. There's an inline filter, and this is a fuel injection type filter. It's made to handle, you know, the pressures 30, 40, 50 psi. This is a sensor, and this is called the MAP sensor. And what this does is this looks at atmospheric pressure, and this is the device that constantly communicates with the computer and tells it what the barometric pressure is of the air, so that it knows how much fuel to give. This is the device that as your airplane flies and gets to higher altitudes, this constantly communicates with the computer to constantly correct the fuel mixture. So this device right here is why you do not have a mixture control on the dashboard of your airplane anymore. It's totally automatic. Of course, there's the gold box. That's the ECM. And here is a simple GM air temperature, and this would normally be mounted in where the air filter is, so that the computer can look at the temperature of the air that's entering the engine. It helps in calculations to correct fuel mixture. Okay. There is a relay here that comes with the kit, and this relay right here is the relay that turns the electric fuel pump on and off. The ECM does not like to carry large amounts of current, so it actually controls relays, and the relay itself is what turns the fuel pump on and off. This blue device is an aftermarket voltage regulator. It's capable of handling 16 amps, and since we're using the 084's permanent magnet alternator, this permanent magnet alternator produces AC voltage, which comes down here and is rectified into DC, and it also does the voltage regulation, and the wires coming out of it are connected directly to a small battery. So that is between the alternator and the regulator, that's the electrical charging system of this airplane engine. Here you see the throttle body, and over here on the left hand side is the throttle position sensor, and this is what tells another sensor that tells the computer basically what's going on with the throttle. And when you open it it tells the computer to add extra fuel at the injectors to simulate an accelerator pump, so you don't get any stumbling or anything when you hit the throttle. If you look here, this is the control that opens the butterfly. This is the throttle. Okay, and you can see that that shaft that's there is connected directly to the throttle position sensor. On the fuel rail, I have a fuel pressure gauge, and this fuel pressure gauge is just that. It tells me what the fuel pressure is. In an actual flying airplane, this would stick out of the cowling and be pointed back at the pilot, just so that you can look up and see what the fuel pressure is doing. A increase of fuel pressure would indicate restrictions, and a lower than normal fuel pressure would indicate quite possibly that the battery voltage is getting low. There are several things that are monitored by the computer here, and one of the things is battery voltage. There is a warning indication if the battery voltage starts to get low, and that happens considerably sooner than the engine would actually quit. So if you start getting a battery voltage low indication, you still have 15 or 20 minutes to find a place to land before the engine quits. Here is another sensor that's on the engine. This is the permanent magnet alternator, and there is an aluminum disc that's bolted to it. And in this aluminum disc are two magnets. I don't know if you can see, but there's a magnet right there, and then directly across from it there's another magnet here. And when this rotates, they pass in close proximity to this sensor, and that tells the engine several things. Now, one of the things it tells it is engine RPM. Another thing it tells it is when the cylinder banks are coming up on a firing position, so it tells the injectors when to fire. This is not sequential port injection, meaning the fuel injectors on this engine do not activate one at a time. They activate in pairs. So you're basically firing cylinders 1 and 4 and 2 and 3. That is the way this system is designed to work. There is no advantage to sequential port fuel injection until you start getting up in the 6,000 and 7,000 RPM range, which this engine will never ever even come close to that. But sequential port fuel injection would have 5 or 6 more engine sensors than this has. So this is just a basic electronic fuel injection system that is light and has very, very small power requirements, and enables this engine to make reliable horsepower without any tuning or anything. Once this engine is set up and the fuel injection system is programmed, there's nothing else you have to do to it. Just start the engine. You basically flip the system on and prime the engine and turn the ignition on, and you flip it and it's running. It is just like your car engine in the respect that this system constantly monitors air temperature. So when this engine is cold, it runs just as good cold as it does hot. It constantly adjusts mixture, so there is no choke. So normal starting of this system is you basically turn the ECM on, which turns the fuel pump on. Every time one of these magnets passes that sensor for the first 10 times, it actually tells the injectors to spray fuel in the cylinders. Now what this is a priming system, and it is set up right now to where every time I pull the prop through and a magnet passes that sensor, the injectors will open and spray fuel in the cylinders. And it will do that 10 times, and on the 11th time that magnet comes by, it won't do it anymore, because the engine should already be running by that point. But if you need to start over again, you basically turn the ECM off and turn it back on, and then it goes back into that crank cycle again. So I'm going to power the ECM up and pull the prop through one time so that you can hear the injectors adding priming shots of fuel. We're going to make sure that the mags are off, so they're in a stop position, so they're grounded, so there will not be ignition. The ECM and the system is on, so I'm going to pull the prop through one time, and I want you to listen at the injectors. You'll hear the magneto snap, and then you'll hear the fuel pressure prime. I'm going to pull the prop through, and you'll be able to hear the injectors. Hear that? That was the injectors firing, and that gave it one shot of fuel. Okay, I'm going to pull it through one more time and give it a second shot. Okay, I'm going to pull it one more time and give it a third shot. Okay, what we did was we just turned the system on, pulled the prop through, and it just gave it 3 shots of fuel. So if I turn this switch to run and pull the prop through, the engine's going to fire and run. But we're inside, so we're not going to do that. So I'm going to go ahead and move this outside and set everything up, and we'll go ahead and start the engine. Okay, what we're going to do here is engine's outside. It's tied to my trusty pickup. I use this stand for doing pull testing and things like that. I've got a strain gauge inside where I can actually hook up and see how much thrust I'm getting and things like that. This is a 54 by 28 prop. Okay, with this prop, I can easily overrev the engine. A lot of guys that are running the 084 with a carburetor, this is probably a good match for that. In this application, it doesn't load the engine enough. I can easily overrev it. I prefer a 58-inch prop. If you've got the ground clearance to run a 58-inch prop, you get a better flywheel effect. That gives you a much smoother engine, and you get quite a bit more thrust out of it as well. Currently, I am running a 5830 prop, which I can turn in excess of 3,450 RPM. I have a prop that I borrowed from a friend that's a 5832, and that's probably going to be the prop that I end up running on my airplane. That engine I can turn at about 3,200, 3,250 RPM. Thrust in excess of 240 pounds. It's probably closer to 250, which most guys, if they can get 200 to 210 out of this engine, they're doing pretty well. So I figure in the power department, I've made a significant improvement, but that's not the only reason this system's here. This system is reliable. This engine runs incredibly well, and any of the guys who have been using carburetors know that you're constantly tweaking, and you're constantly, once you set this system up, then you just forget it. You just start it and you fly it. You start it and you fly it. I mean, it's just that simple. So engine's cold. I'm gonna go ahead and do a normal starting sequence. I'm gonna turn the ECM and the fuel pump on. I'm gonna pull the prop through a couple of times. You'll be able to hear the injector system priming the engine. Then I'll turn the mag on, and then we'll start it and let it run for a couple of minutes, and then we'll shut down and talk about it. Okay. So right now, I'm gonna turn the fuel system and the ECM on. You'll hear the pump start up. Magnetos are off. They're grounded, so they're off. I'm going to pull the prop through and prime the engine. If you'll listen, you'll be able to hear that priming that I was telling you about happen. Okay, there's one. There's two. We'll go ahead and give it a third prime. Okay. It's about 75 degrees here in North Carolina. It's not a cold day, but this engine starts just as good at 30 degrees as it does at 70. So I'm going to turn the mags on, and I'm going to use 2 fingers, and I'm going to pull the engine through. 650 RPM idle at cold. The engine has not been started today. You'd never get that to do that with a carburetor, ever. That's 500 RPM. Right now, because the engine is going through its cold enrichment process, until the engine gets up to 140 degrees, the computer automatically calculates the fuel needed to make it run smoothly. Right now the idle screw is all the way out, and until the engine gets warm, it won't idle any lower than that because the mixture is kind of rich. So here in a few minutes, I'll let it run and to get it up to temperature, and then we'll see if we can get it on down to a lower idle. While we're waiting on the engine to get up to temperature, I'll go ahead and walk around with the camera and let you see as much as possible. That's the idle speed adjustment right there on the throttle button. I don't know if you can hear that, but it's running extremely slow. I put the camera down so I can walk over and adjust the idle speed. Now that it's warmed up, I'll see how low I can get the idle. In fact, I'll keep lowering it until the engine shuts down. The tachometer says 400 RPM. It's kind of fluctuating around, but it's getting ready to quit. Maybe not. I've got the idle screw all the way out, and the engine's warmed up. You would never idle it that low. I just wanted to show you how good it idles. Now with it idling that low, I'm going to go ahead and rev the engine a little bit just to let you see that it goes from one extreme to the other. I normally lose my hat during this, so you might get something comical out of it. Wow, it stayed on pretty good that time. But anyway, that's a normal low idle there. That's about 600 and just over 600 RPM. And that was full throttle just a minute ago. So as you can see, the engine runs extremely well. I'll go ahead and slowly go through the throttle again so that you can hear it rev up. Okay, so what do you think so far? Looks like it runs pretty good. Let's shut it down and restart it. We'll turn the mag back on and we'll go ahead and restart the engine. I want you to notice something. I'm going to back the camera up. When I accelerate the engine to full throttle, it actually bends the platform that this thing is sitting on. It's pulling so hard. I mean, you can actually see the engine trying to bend forward. It's trying to take off and trying to go. You notice the strut that's closest to the propeller. I had to put that there because it would actually bend the motor mount forward at really high power settings, and it just made me nervous. So I put that strut there to keep it from going anywhere. I'm going to back the camera up and watch the platform. Mag's hot. Clear. Clear. normal 600 to 650 RPM idle. I'm going to increase it. Run it up to about 1800 and let it sit there for a minute. I actually have an air bleed on the idle here, where if this was in a car and you turn this on, it would be like turning the air conditioner on your car, so it needs to idle up just a little bit when you turn your AC on. I use it to go from idle to, you know, about 1800 RPM. It's just a little cap I remove and it'll go right to 1800. What I call a high idle. On a fuel-injected system, a leak in the intake manifold produces high RPM, because remember, we're controlling air. So if you've got an air leak somewhere in the system, you actually cause the RPM to increase. That cap that I just took off is a vacuum port, and if you uncover that, it allows air to bypass the butterflies and increase the RPM. So the computer looks at airflow. Whatever the airflow is, it does whatever it needs to do to adjust fuel mixture. So by opening the butterflies, it looks at the volume of air and adds just the right amount of fuel to create the ideal mixture. So an intake manifold leak, with one indication of that would be RPM that you can't control. So it's just a rubber plug. When I remove it, the engine goes to 1850 RPM. Well guys, that's about it. Again, my name is Les, and I'll end up here by just telling you a little bit more about the engine. This is a stock 0-time 4084. I pulled it right out of a generator, pulled the sheet metal off, added a prop hub, removed the intake spider in the carburetor, and built this very simple fuel injection system for the engine. This engine has stock compression, which is about 7.5 to 1. A lot of guys like to up the compression to try to get more power out of them, but that's the wrong way. An airplane engine is not an automobile engine. So increasing the compression ratio, yep, it does increase the power, but there is a side effect of that. You create a lot of heat in the cylinder head, and this is an air-cooled engine. It's not meant for short bursts of speed. An aircraft engine is under a constant load all the time. It has to be working to keep you in the air. So engines with high compression have a tendency to overheat after a short period of time. At full throttle, max power, this engine cylinder head temps get around 420 to 425. That is right where they should be. 450 is the red line, and I have a 5-minute rule. If I ever exceed 450 degrees, I limit that to 5 minutes. In my opinion, that's perfectly safe. I've torn apart thousands of these engines over the years, rebuilding them for generator engines in the military. Air-cooled engine can handle that. But anyway, here is an engine that thrust-wise, and I do realize it's a little bit heavier, but thrust-wise, it's in the league of a Rotax 503, which is pretty substantial. It's approximately 50 horsepower, 230 to 240 plus pounds of thrust is easily achieved, and then a 300 or 400 pound airplane such as a J3 Kitten, a Cub, an M3 Pup, those style airplanes, something that probably doesn't exceed 750, 800 pounds. This is a great little engine package. I see 1,500 hours plus easily achievable on these engines. The last two engines that I've been running for some time, I've pulled several of them apart and have found no abnormal wear. So anyway, here it is. And you know, a lot of people made the comments about putting a $1,000 fuel injection system on an engine that we pay about $300 or $400 for. But if you look at this engine in real money, this is a $5,000, $6,000, $7,000, $8,000 engine easily in today's money, and you can't buy one that cheap. It is the Volkswagen's little brother. This engine, as it sits right here, weighs 126 pounds. So the only thing that I would do any different with this engine would be I would get rid of the big heavy oil filter that's on it and build something smaller. But other than that, this engine right now could be bolted right in the airplane and go fly. Well, I hope you found this informative. If you have any questions, don't hesitate to ask. It's something that anybody with a little bit of patience and some basic skills could put together very easily. Thanks a lot.